We're going to begin part 2 of our discussion on chemical equilibrium by attempting to solve some problems. Get your calculators out, folks. It's about that time. We focused on the idea of the equilibrium constant and the value that it must have in order for a reaction to be considered at equilibrium. For any given reaction mixture, if we take some products, some reactants, and allow them to come to equilibrium, that ratio of products to reactants must be achieved. So how do we know if a reaction is indeed at equilibrium? And if the reaction is at equilibrium, what does that say about the relationship between the equilibrium constant and those equilibrium concentrations, the amounts of substances at equilibrium? Well, these things are tied together mathematically in a way that we're soon going to find ourselves enveloped in. So on your mark, get ready, get set, go. In order to understand the relationship between equilibrium concentrations and the equilibrium constant, for a particular set of circumstances, we need to tabulate all of the data that we know. A reaction undergoes a change. We start out with initial concentrations or an initial amount of reactants and products. Over time, changes occur. And after those changes occur, we have reached equilibrium. So there are steps in order to deduce the equilibrium concentrations associated with a particular set of circumstances. The first thing we need to do is to tabulate all known concentrations, whether they are initial concentrations or equilibrium concentrations. If there's anything that we know both the initial and the equilibrium concentrations for, then we can determine how our concentration changed. For example, if we know that the initial concentration of nitrogen dioxide was 0.500 molar, and we know that over the course of a reaction, we end up with an equilibrium concentration of 0.322 molar. We know how we started, we know how we finished. The change that occurred was that we lost 0.178 moles of substance per liter of sample. So, if you know the initial and the equilibrium concentrations, then you can calculate the change. And those three things are tied together in what we call the ICE method, where I stands for initial, C stands for change, and E stands for equilibrium. Now, once we have established what we know, we can use the balanced chemical equation to find the change for any other reactants or products. For example, if we lost 0.178 moles of nitrogen dioxide, our stoichiometry would suggest that we would gain a certain amount of product. If the product were N2O4, then stoichiometrically with a 2-to-1 molar ratio, we should be able to determine how much dinitrogen tetroxide is formed. Now, if we know the initial concentrations and the changes that occur, then we can find the equilibrium concentration of all the species involved. From there, we can calculate the equilibrium constant since we have all of the concentrations of our products and reactants at equilibrium. And if we need to, we can use these steps out of order. If we're given the equilibrium constant and we need to deduce something in terms of the initial conditions or the equilibrium conditions, we can use the mathematical relationships presented here in order to answer those questions. Here's an example. A closed system initially containing 1.000 times 10 to the minus 3 moles per liter of hydrogen and 2.000 times 10 to the minus 3 moles per liter of iodine existing at 448 degrees Celsius is allowed to reach equilibrium. Analysis of the equilibrium mixture shows that the concentration of hydrogen iodide is 1.87 times 10 to the minus 3 molar. Calculate the equilibrium constant at this temperature for the reaction taking place. And the reaction involves the homogeneous equilibria of elemental hydrogen reacting with elemental iodine in order to form hydrogen iodide gas. Now, based on this information, we tabulate everything that we know. We look at the initial concentrations of our reactants. We know that since we have no hydrogen iodide at the beginning of the reaction, that our initial concentration of HI is 0. We know that at the end of the reaction, we have a certain amount of hydrogen iodide that is formed, specifically 1.87 times 10 to the minus 3 moles per liter. So since we know the initial conditions and we know the equilibrium conditions, we know how this particular component of the reaction has changed in concentration. Our hydrogen iodide has increased in concentration by 1.87 times 10 to the minus 3 moles per liter. Well, that just goes without saying. If we started with none and we ended up with some, then how did it change? We added some. We see the formation of some. Now, if we take into consideration the stoichiometry of the equation, we can deduce the change that occurred in our hydrogen concentration as well as our iodine concentration. If we see the formation of 2 moles of hydrogen iodide, it is because of the consumption of 1 mole of hydrogen and 1 mole of iodine. Stoichiometrically speaking, there is a 2-to-1 molar ratio of hydrogen iodide to hydrogen. There is a 2-to-1 molar ratio of hydrogen iodide to iodine. Therefore, the amount of hydrogen that was consumed is going to be half that of the amount of hydrogen iodide that was formed. If we see the formation of 1.87 times 10 to the minus 3 moles of hydrogen iodide per liter of space, that means that we have consumed half as much hydrogen, half as much iodine in terms of what's essentially 0.935 times 10 to the minus 3, or 9.35 times 10 to the minus 4 moles per liter. It's important to note that this change is a subtraction. We started with reactant and we lost reactant. Well, if we know how we start and we know the change that occurred, we know what happens at equilibrium. If we know that we initially started with 1 times 10 to the minus 3 moles per liter of hydrogen, and we lost 9.35 times 10 to the minus 4 moles per liter, we know what our equilibrium concentration is. Similarly, if we lost a stoichiometrically equivalent amount of iodine, we know how much iodine exists at equilibrium. Now it appears that we know our equilibrium concentrations of all 3 components: our hydrogen, our iodine, both reactants, and our hydrogen iodide as a product. If we simply apply our K sub C expression, then we should be able to determine the equilibrium constant for this reaction at this particular temperature. Since the equilibrium constant expression speaks of products over reactants stoichiometrically weighed as coefficients, then we input those values into this expression. When we find our hydrogen iodide concentration, we square it based on the stoichiometry of our equation. And we divide that by the concentration of hydrogen times the concentration of iodine. In doing so, we end up with a value of 51. So the equilibrium constant for this particular reaction at this particular temperature is simply 51. Now, there are two things to take note of with respect to the equilibrium constant. The value of K changes with respect to temperature. That's why with the previous reaction, I spoke of the reaction taking place at 448 degrees Celsius. At room temperature, the reaction does not occur because iodine at room temperature is indeed a solid. At elevated temperatures, we see iodine in the gas phase. And at these elevated temperatures, we see the reaction mixture of products and reactants differ based on temperature. The value of K is very much temperature dependent. So if you're calculating the K value for a particular reaction, make sure that you note the temperature at which the reaction occurs. Now, that temperature doesn't factor into any particular equation with respect to K sub C. But it should be noted that if we perform the hydrogen iodide production reaction at a higher temperature, we're going to see a different value of K sub C representing that equilibrium mixture. Also, and it pains me to say this, but K sub C, the equilibrium constant, is a unitless constant. I just can't say anything else there. I'm the guy who says numbers without units are meaningless in measurement. Well, this relationship that is K sub C is actually based on a mathematical expression that refers to something called the activity of a particular substance. Now, without going into all of that, all you need to know is that K sub C is unitless. And I weep. Now to determine if a reaction is indeed at equilibrium. Now we know in the previous example, once equilibrium had been established, that the reaction was at equilibrium. But until that point, the reaction was going to proceed towards equilibrium. The question is, how do we know if a reaction is indeed at equilibrium? And if so, how is it going to proceed? Are we going to see the forward reaction proceed in order to reach equilibrium? Are we going to see the reverse reaction become more dominant in an attempt to reach equilibrium? Well, in order to answer these questions, we calculate a ratio known as the reaction quotient. Now, the reaction quotient is represented by the letter Q, capital Q. The expression for the reaction quotient looks just like that of the equilibrium constant. In other words, we're looking at the ratio of products to reactants, stoichiometrically weighed as coefficients. The only difference is the equilibrium constant is going to remain a constant for a given temperature. But the value of Q can represent any set of conditions, whether the reaction mixture is at equilibrium or not. In short, reactions tend to proceed towards equilibrium. So at the end of the day, the universe is happy when our value of Q is equal to K, when the ratio of products to reactants, stoichiometrically weighed as coefficients, is equal to the equilibrium constant. So if we were to take a sample of hydrogen and iodine and hydrogen iodide gas and place them in a container, if we looked at those concentrations at 448 degrees Celsius and we saw that those ratios equaled 51, then the reaction mixture would be at equilibrium. If they do not equal 51 when we put it into that expression, then we know the reaction is not at equilibrium, and the reaction is going to proceed in such a fashion that will make equilibrium. So how do we know whether the reaction is going to proceed to the left or to the right? Well, we simply look at what the value of Q is with respect to K. If Q is less than K, that means that the ratio of products to reactants is too small. The only way to make a ratio larger, well, there are actually two ways. You can make the numerator larger, or you can make the denominator smaller. If we find products in the numerator and reactants in the denominator, then I guess the two ways that we could make Q larger would be to increase the amount of products or decrease the amount of reactants. Well, the crazy thing is, both of those mean the same thing. If you decrease the amount of reactants, it means that they are forming more products. So if Q is less than K, then the reaction is going to proceed from left to right, the consumption of reactants and the formation of products. If Q turns out to be greater than K, that means that our ratio of products to reactants is too large for an equilibrium mixture. Then the reverse must be true. Our numerator must decrease in order to make that quotient smaller. Our denominator must increase. The numerator decreasing means that products are lessened. The denominator increasing means that reactants increase. So we would see the formation of reactants and the consumption of products. The reaction would proceed from right to left in order to reach equilibrium. Now things tend to get a little bit more complex. If we're trying to calculate our equilibrium concentrations, if you know the equilibrium constant, then you can calculate those concentrations based on initial conditions and the changes that occur. There's going to be unknowns. If we don't know the equilibrium concentrations of our products and reactants, then there are unknowns. So we would similarly set up our ICE table with the initial conditions, the changes that occur, and the equilibrium conditions. And we would ultimately represent our equilibrium conditions as an unknown. Typically, mathematically speaking, X generally represents the unknown. So let's take a look at a problem in which we attempt to determine the equilibrium concentrations of our products and reactants when given initial conditions. For example, a 1-liter flask is filled with 1 mole of hydrogen and 2 moles of iodine at 448 degrees Celsius. If we're given a K sub C value of 50.5 at 448 degrees Celsius, then what are the equilibrium concentrations of hydrogen, iodine, and hydrogen iodide, respectively? In other words, if we place some reactant into our reaction vessel, product is going to be formed. How much product is going to be formed? Well, if we don't know, then we have to represent that as an unknown. And if we don't know how much is formed, then we don't know how much of our reactant is lost. So that will similarly be an unknown. So we're going to take our unknown value of X to represent the change in concentration of hydrogen. We know that over the course of this reaction, since we have some hydrogen and some iodine, and we end up with some hydrogen iodide, that the hydrogen and the iodine, or the iodine, depending on how you care to pronounce it. I prefer iodine, but that's just me. We're going to see a decrease in the amount of hydrogen and iodine and an increase in the amount of hydrogen iodide. The only thing that we know are the initial concentrations of our 3 reaction components. We set our change in concentrations based on our unknown. We know that we lose some reactant. We know that we gain some product. And stoichiometrically speaking, we see a 1 to 1 to 2 molar ratio of our reactants being lost to our product being gained. If you know the initial concentration and you know the change in concentration, then similarly, we can determine our equilibrium concentration. The only problem is now each of those terms has that X associated with it, and we still don't know what X is. But given a case of C value of 50.5, with the previous example, we rounded that to 51. Can we determine what X is? And the answer is, well, sure we can. We set up our equilibrium constant expression the same way that we have before, representing products over reactants stoichiometrically weighed as coefficients. Now, our concentration of HI is represented by 2x. Our concentration of hydrogen and iodine are represented by 1 minus x and 2 minus x respectively. So the ratio of products to reactants stoichiometrically weighed as coefficients is going to equal our K sub C value, which is 50.5. At this point, here's where the math can get fun. In order to figure out what X is, we're going to have to use the quadratic equation. Because by expanding those two terms in the denominator, we're going to see the introduction of not only a numerical term, but also an x-based term, as well as an x-squared based term. So if we have an x squared and an x and a constant or a numerical term, in order to solve this type of equation for x, we have to employ the quadratic equation using your textbook to solve the quadratic equation where x is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a, gives us an x value of either 2.323 or 0.935. Now, a few things should be noted with respect to the quadratic formula. Since we are in fact solving the quadratic formula, we're going to get two answers for what x can be. These are called roots. Well, one of these roots is going to be useful and one of them is going to be extraneous. For more information on using the quadratic formula and how to solve this particular type of problem, feel free to consult your textbook or see me face to face and talk to your good old professor. Since our value of x must be subtracted from 1, since it must be subtracted from 2, the value of 2.323 doesn't make any sense. You cannot have a negative concentration. If you start out with a 1 molar sample of matter, you cannot end up with a negative molar sample of matter. You either have that amount or you don't. So the 2.323 represents an extraneous root, one that is not useful. The other value that comes out of the quadratic equation must be the useful one. So 0.935 is the value of x for this particular reaction. Now, if in fact 0.935 is our x value, then when we subtract that from 1, we get 0.065. When we subtract that from 2, we get 1.065. And when we take our equilibrium concentration expression, we look at the equilibrium concentration of hydrogen iodide, which is going to be 2 times x, which for this example results in an equilibrium concentration of 1.87 moles per liter. So we've essentially used our equilibrium constant in order to determine our equilibrium concentrations, whereas before we used our equilibrium concentrations in order to determine our equilibrium constant. Sometimes you need to use the quadratic equation in order to solve this type of problem. Sometimes you may not have to. The last portion of this chapter is dedicated to a concept known as Le Chatelier's principle, named after Henri Le Chatelier, a French chemist in the late 19th century. What Le Chatelier's principle essentially tells us is that a system at equilibrium, when a change is introduced that disturbs that equilibrium, the system is going to do its darndest to reestablish a new equilibrium. If a system is currently at equilibrium and you do something to change it, whether that change represents a change in temperature, a change in pressure, or a change in the concentration of a reactant or product, then the system is going to shift in order to reestablish equilibrium. Well, let's see what that means on an individual basis with regards to the things that can be considered disturbances to a system at equilibrium. If we see a change in the concentration of either a reactant or a product, how is that going to affect the position of equilibrium? Well, if we have a system at equilibrium, that means we have a set amount of reactant and product. If we add reactant to that reaction mixture, then the system will recognize that there's too much reactant now. The reactant must be consumed in order to reach equilibrium. So by adding reactant to a reaction mixture at equilibrium, the system is going to try to get rid of that by forming more product. If you add product to a reaction mixture, let's say we have that previous example of hydrogen iodide and hydrogen and iodine at equilibrium. If I were to open up the system and add more hydrogen iodide to the system, the reaction mixture is going to say, oh, wait a minute, I've got too much product. I need to get rid of some of it and form some reactant. Similarly, by removing a reaction component, it must be replaced. If we get rid of some product, the system is going to say, wait, I don't have enough product. I need to replace it. So we're going to see the formation of more product. If I were to remove all of the hydrogen from a reaction mixture that contained hydrogen, iodine, and hydrogen iodide, the system is going to say, wait a minute, I don't have enough hydrogen in this reaction mixture. I need to see the formation of more reactant. So the system is going to change in order to replace or get rid of any reaction component that has undergone a change. Now, if we see a change in volume or a change in pressure, and we know the relationship between volume and pressure of a gas is inversely proportional, a reaction mixture at equilibrium is going to favor forming more moles of gas if introduced to a higher volume. In other words, if you expand a gaseous system, then the reaction that favors the formation of more moles of gas is going to take place more readily. In the equation seen here, we see the formation of B from 2 moles of A. By expanding the system, we're allowing for a greater volume. a larger volume is going to favor the side of the equation that has more moles of gas. So by increasing the volume, we're going to see the formation of more moles of gas. In other words, the reverse reaction is going to take place. B is going to form 2 moles of A. If we instead compress a system, resulting in a change in volume that is a decrease, well, now the system is going to be stressed in such a fashion that fewer moles of gas are going to form. So the reaction will proceed from left to right so that fewer moles of gas occupy the container. Well, how does a change in temperature affect equilibrium? Well, it depends on whether the reaction as written is an endothermic reaction or an exothermic reaction. If you think of an endothermic reaction as one that involves heat being introduced, then heat essentially acts like a reactant. A plus B yields C. If that's an endothermic reaction, then A plus B plus heat will yield C. For an exothermic reaction, we see that heat acts like a product. If the reaction were X plus Y yields Z, and the reaction is exothermic, then it could be considered as X plus Y yields Z and heat. So if we consider heat to be a component, like a reactant or a product, then adding heat or changing the temperature, increasing the temperature, is going to be like adding that particular component. For an endothermic reaction, heating it up drives the reaction towards the product. Why? Because the system says, oh, now I have too much heat. I've got to get rid of it and form some product. Adding heat to an exothermic reaction says, okay, wait a minute, I've added product. I now have to see a shift towards the formation of reactant because now I have too much product. Removing heat behaves in the same way that removing a reactant or removing a product would. So cooling a reaction down is going to favor an exothermic reaction. In chapter 14, we introduced the concept of catalyst. Catalysts are substances that increase the rate of a chemical reaction. Well, the role of a catalyst in an equilibrium system is that, yes, it will indeed increase the rate of reaction. But not just the rate of one reaction, it will increase the rate of both the forward reaction and the reverse reaction. So ultimately, our equilibrium point is achieved faster. But the equilibrium concentrations do not change. In other words, we get to the finish line faster with a catalyst, but it doesn't affect where the finish line is. The catalyst acts by lowering the overall activation energy, or the amount of energy that's required in order to establish a reaction. And that allows equilibrium to be established at lower temperatures. What is the effect on equilibrium of adding a catalyst in terms of Le Chatelier's principle? Absolutely nothing. A reaction at equilibrium will not respond to the addition of a catalyst in a shift to the left or to the right. Well, that, ladies and gentlemen, is the end of our chapter 15 adventure. Hopefully, we've learned a little bit of something about equilibrium. It is my great hope that we've learned a lot about equilibrium. Take care, and as always, stay safe.